Hi, this is chapter 16 on food additives. This is a two-part chapter, so this week we'll be covering pages 459 to 469, and then next week we'll cover the rest of the chapter. Then an additive, let's talk about some ingredients first. Ingredients and additives are not necessarily the same thing. The ingredients are component parts of food products that are generally recognized as safe. So the ingredients in bread, you have flour, water, salt. Okay, those are ingredients. Whereas additives are substances added to a food to cause some desired positive change in the product's characteristics. There are two types of additives. The first is intentional additives, and these are the additives that we purposely add to get the desired positive change. Then there are also incidental additives, and these are additives that get into a food unintentionally, and they actually might be positive or negative. So these incidental additives could be put in the food at any point from the farm where the fruit, vegetable, meat, whatever, is grown to the kitchen table. The intentional additives, I'll go back, they can be added on to give specific characteristics to, they can be used to improve shelf life, reduce spoilage, improve food safety. The incidental, these are things like the book gives the example of wax in milk cartons. The milk carton is wax lined so that the moisture doesn't escape, because a paper milk carton and moisture is not a good combination, so they line it with wax to keep the moisture in. But some of that wax may flake off and get into the milk, and it doesn't cause any harm. Another example would be bugs in vegetables or nuts. These are things that are part of the environment where those products are harvested, and they can get into the food unintentionally. And there's a certain level that is allowed and acceptable. A third example would be BPA, which bisphenol acetate, I think is what it is. And that's in canned vegetables. So those cans are lined with BPA, and kind of similar to the wax, it's lined with that so that the food product doesn't come in contact with the metal. In this case, it's because they would be worried that the metal would corrode. For example, if you have canned tomatoes, which are highly acidic in the can. Now, because this one is really negative, and they've discovered that BPA in our body system is not a good thing, this one isn't used very much anymore. So it's actually not something that you really need to worry about in your canned vegetables, but it would be an example of an incidental additive. Okay. So the Food and Drug Administration, also known as the FDA, has authority over most food and ingredients. About 80% of our food and ingredients in the food supply are controlled by the FDA, regulated by the FDA, I should say. The exception, the other 20%, is controlled by the USDA. Okay, so FDA and USDA regulate the food supply. USDA controls meat, poultry, catfish, so only catfish, and that is because all the catfish that are sold in the U.S. are like farmed in the U.S. And I couldn't really tell you why that's different from farm salmon, for example, but for some reason USDA has control of catfish only. Process eggs, so these are not eggs in the shell, but as soon as you take them out of the shell, if it's liquid egg product or you've powdered eggs, these are controlled by USDA. eggs in the shell are controlled by FDA. USDA also regulates dairy and fresh produce. Now, as soon as you've done anything to process that produce, it is now FDA. So if you have dried fruit like raisins or prunes or apricots, now it's FDA. But if it's fresh, USDA regulates that. This all started in part from 1938, at least with the FDA, the Federal Food, Drug, and Cosmetic Act, and that gave FDA authority over these foods and ingredients. It also defined requirements for truthful labeling. So you can't say that your product is something that it is not. And this act is overall the basis of US food law. So some guidelines for the uses of additives legally starts with the Food Additives Amendment that was in 1958. And that amendment to the Food, Drug, and Cosmetic Act said that no additive can be used in foods without FDA approval. In this case, to get FDA approval, the manufacturer has to provide the proof of safety. And that's just putting more onus on the manufacturer to pony up the money to provide this proof, because the government does not need to be spending all kinds of money on additives that may or may not be worthwhile at all. So I will say that's kind of a catch-22, because the manufacturer who has, a dog in the fight to get that approved is the one that is providing the proof. So it's plus and minus, because the government doesn't need to be spending money and going on wild goose chases proving things that may have absolutely no chance of being approved. But again, it's an issue where the manufacturer, of course, has incentive to get it approved, and they're the ones providing the proof. So it's good and bad. With that proof, the FDA determines the margins of safety, and that is the zone between the concentration at which the additive is normally used. So let's say I normally will add this to my product at 5% of the product, or 1%. If I accidentally added more, at what point does it become unsafe? And so that is the margins of safety, the zone between the concentration at which the additive is normally used and the level at which a hazard exists, the level at which it becomes unsafe for consumption. So in order for an additive to be approved, there are several requirements that it must meet. It must perform a useful function. And I would know these, not necessarily memorize them, but recognize them, which of these are requirements and what maybe wouldn't be a requirement. The additive cannot be used to deceive the consumer or cover up faulty manufacturing practices. So on Facebook, I've seen things like, why is this meat red? And this is what I got from the store, but this was from the farm, and this one is turning brown, or something like that. And they imply that there's dye in the meat. Well, that's illegal. You cannot use any additive to deceive a consumer. So you can't use dye in meat. And in fact, there are regulations even in processed meats where you can't use things like paprika, which is a red coloring, to change the color. If the purpose is only to change the color, you can't use it. So you also can't use things to cover up faulty manufacturing practices. So you can't use something just to disguise the smell or bad taste of something if it's due to a bad manufacturing practice and the product is spoiled, for example. The additive cannot cause a substantial loss of nutritive value in a food. So a good example would be from the last chapter that we covered with Olestra. The Olestra does cause a loss of nutritive value of vitamins A, D, E, and K. And so what they had to do to fix that is add more back in. And that is how they got around this. They increased the nutritive value to not cover up, but to make up for the loss of nutritive value. So there was not a net loss of nutritive value in that food using that additive. It cannot be used in place of good manufacturing practices. So you can't say, well, instead of properly cleaning my equipment and making sure bacteria don't get into my food, I'm going to use this antimicrobial that'll kill everything. You still have to have good manufacturing practices, which what those are just general practices that you have in your facility to make sure that everything is clean and safe. And finally, a method must exist for analyzing the presence of the additive in the food. So you have to be able to analyze and detect how much of the additive is in that food so that in the case where you did accidentally add too much, for example, or too little, you can test for that and determine if it is at an unsafe level. So another important thing that came about with FDA and the regulation of additive is the GRAS list. And GRAS stands for Generally Recognized as Safe. This list currently is about 370 ingredients that are additives that are considered safe at the levels currently used. But these additives don't have a regulation with them. There are no set levels where you must have the amount of this additive at or below this amount to use it in the food. There's no regulation around it. But they've determined that as long as you follow current practices, it is safe. And so with that, they've also determined, okay, let's go back here. That margin of safety is large enough that we really don't need to be concerned about it because manufacturers use it at this current level and they're never going to get close to reaching the upper end of that margin of safety. And so that's why those are considered generally recognized as safe. On the other hand, we have controlled use substances. So we have the generally recognized as safe substances and the controlled use substances. These are the ones that are not on the GRAS list. And there are over 3,000 additives that are on this list of controlled use that have been approved for use in foods. And if the substance is controlled use, then the FDA does, or USDA, dictates exactly how much of an additive can be added to different foods. And it may be different for different foods. Often, these substances are added in parts per million. And so what that means is that for every however many parts by mass, there must be 1 million parts of the rest of the food by mass. The book has this incorrect. I think it says by atoms or particles, and that is usually not how it is measured. That is a possible way to measure parts per million, but that's not, trying to think of the right word. that wouldn't make sense to use in the food industry, because nobody is calculating the mass by atoms, by molecules in the food products. So instead, they're just doing an overall by mass. Somebody has pre-calculated all of that molarity and things, and rather than having to go back and calculate that and make it even harder and more chance of making a mistake, you just say by mass, by overall mass. So that for every 1 gram of this substance by mass, there must be 1 million grams of the rest of the food by mass. That would be 1 part per million. For every 250 grams by mass, there must be 1 million grams of the rest of the food by mass. That would be 250 parts per million. Okay. And so as you can see, a lot of these substances, if we're measuring it in parts per million, they are added in very, very small amounts and regulated to that level. Otherwise, they could become dangerous. Another important regulation in regards to food additives is the Delaney Clause, and that is an amendment to the food additives regulations, which bans the use of any food additive known to cause cancer in humans or animals. There are some problems with the Delaney Clause, which were discovered a little while after the clause was introduced, and that is that the products might cause cancer in animals, but not humans. And if it doesn't cause cancer in humans, does it really matter if it's in the human food supply? And that answer is probably not. Also, technology can detect additives in cancer at much lower levels now. And so if we can detect cancer at the tiniest level, well, that's not the same as back when this clause was introduced and we knew for sure this causes cancer, right? And so it really, if you're being very strict with this clause, it reduces a lot of the foods that the additives that can be used. Finally, it's impossible to keep all carcinogens out of food. Many substances can cause cancer if eaten enough. And that even includes sugar, right? Sugar and high carbohydrate diets can cause lots of inflammation in your bodies. There's evidence that milk causes inflammation in your body, and inflammation leads to cancer. So it really is impossible to keep all carcinogens out of food, because anything, if not eaten in moderate quantities, can cause cancer. So instead of strictly following this clause, we have to be more reasonable about it. And so the FDA considers an additive safe if the risk of cancer is 1 in a million or less. And that's more reasonable than very strictly following this clause. If substances are required or cannot be avoided, regulations are established to limit quantities as much as possible to protect public health. So there are some additives where there is no other alternative. This additive keeps the food safe. There's no other alternative that is known to replace it with. And so there's regulations to limit the quantities as much as possible. So it can still be in the product, but the risk of cancer is very low. There are 4 functions of additives that we'll be going over. We're actually only going to go over the first one in this lecture, and then we'll pick up the other 3 in the next lecture, just kind of how the book was divided for this chapter. So the first function is to preserve product quality. Next, to enhance sensory characteristics. To control product consistency. and to improve or maintain nutritive value. So we're just going to go over the first one, preserve product quality, in this lecture. So essentially what we mean as far as additives and preserving product quality is preservatives. Preservatives are any substance that's added to a food to prevent or slow spoilage and maintain natural colors and flavors. So there's two main forms of spoilage that we're concerned about. The first is microbial. So this is due to bacteria, fungi. So specifically, we're usually looking at mold, not mushrooms, right? So mold growing on food, and yeasts. So yeast can grow on foods where it's not desired and cause flavor and texture issues. The second main form of spoilage would be oxidation. And so we've talked about that quite a bit as far as, especially in fruit, when we talked about enzymes. And so oxidation causes this, right? In our avocados, that phenolase causes browning and other texture changes that are undesirable. In meat, oxidation causes the meat to turn brown. So this picture is one that I found in a search, and it's somebody in Reddit that was like, this meat, it doesn't smell or anything. It's not that old, but it looks like this. Can I still eat it? And what has happened here is that this part of the meat, especially, not as much this, but it got exposed to low levels of oxygen for an extended length of time, and this part has oxidized. The myoglobin, which is the meat color pigment, has oxidized to what's called metmyoglobin, and metmyoglobin is brown in color. So yes, this meat is perfectly safe to eat, but it has oxidized and it's an unappetizing color, and most likely the fat around it has oxidized too, and around this part is not going to be an appetizing flavor either. It's going to taste kind of like if you have a steak and at a restaurant, and then you take it home, and then 3 or 4 days later you microwave it. It's just not very good anymore. And that is what oxidized flavor is. So now we'll go through some antimicrobial agents that are commonly used. The first one here is salt and sugar. And these are our oldest antimicrobials. They've been used for centuries. And essentially how salt and sugar work as antimicrobials is they draw water from the food and also from the microbes, and it essentially dehydrates the microbes. The water is unavailable to them, preventing their growth. Now, salt and sugar are considered ingredients, not additives, so they would not be listed under the GRAS list or the controlled substances list because they perform many functions, including flavor, and of course they're very, very safe to add. You could eat straight salt and sugar. At some point, salt is self-limiting because the flavor is too much, but you can eat them and there's no ill effects. But they perform many other functions, including flavor, right? So jam and jelly, well, obviously that sugar performs a major flavor function in those foods. And salt also. So examples for salt, where salt is the main antimicrobial agent, would be beef jerky. It would be salted fish, which is what this is. So these fish have not been cooked and it's just been salted, and they're dry and perfectly shelf stable and ready to eat. Country hams also, country hams are not cooked. They are just preserved with salt. Jerky is usually cooked to a small degree. And then, of course, jams and jellies on the sugar side are a good example of products that use a sugar antimicrobial as an antimicrobial. So another example of an antimicrobial agent is nitrites. So this is sodium nitrite, which is used, and that's NaNO2, which is different from what the book tells you. The book gives NaNO3, which is sodium nitrate. Very related, but not the same thing. And the reason that we use nitrites is to prevent Clostridium botulinum. It also prevents Clostridium perfringens, so I could say it just prevents Clostridia. But botulinum in particular is the bacteria that causes botulism. And unfortunately, this can be a big deal in meat if not controlled for. Sodium nitrite is responsible for the pink color and flavor of cured meat. So everything from sausage, bacon, ham. I mean, these are all different types of sausages and hams here. Anything that is pink after it is cooked has sodium nitrite in it. So there are some issues with nitrite and reasons it has to be regulated. And that the main thing is that excess nitrite can interact with amino acids, which are abundant in meat, and form nitrosamines during either digestion, so essentially high acid, or high temperatures. Nitrosamines are carcinogenic. They can lead to cancer. And so because of this, the levels of nitrite added to meat products is very carefully regulated. Most of the nitrite that is added to the meat product is actually converted to nitric oxide during cooking. Now, if there's too much of it, then you will have that has been added, then you will have excess nitrite still in the meat. But the way that they regulate this, most of it is converted to nitric oxide during cooking, and you have very little excess nitrite in the meat. Okay, and nitric oxide, the way that works is nitric oxide then binds to the myoglobin, and that is what leads to the cured pink color in the meat products. The levels are regulated based on the product. So some products have more allowable nitrite than others. Bacon has the lowest, and that's at 120 parts per million. Sausage has 156 parts per million, and ham has 200 parts per million. So why are these levels set the way they are? Well, bacon is the lowest, and it is heated to the lowest temperatures in processing, right? It's actually not cooked, right? But in the home or in the restaurant or whatever, it's cooked to a very high temperature. Okay, so bacon has the highest likelihood of forming nitrosamines because high temperature causes nitrosamine formation if there's excess nitrite. And so they add the lowest amount to bacon so that almost all of they're ensuring that almost all of that nitrite has been converted to nitric oxide. So there's so little left over in the bacon that you don't have this nitrosamine formation, which is much more likely with a bacon cooking process because that bacon is fried and cooked at such a high temperature than other products. So bacon is the lowest for that reason. Sausage is a little bit higher. Ham is the highest, and that's maybe for a couple reasons. It's going to get heated cook from a cooked standpoint, right? So bacon is cooked at the end in the home, but ham is usually cooked in the food processing facility. It's going to be heated not necessarily to the highest temperature versus sausage, but the biggest thing for ham is that it needs more Clostridia control. It is the biggest Clostridia risk. Clostridium perfringens and botulinum, they're both anaerobic. They both like no oxygen, okay? And if you think about a sausage, you have ground meat where air has been introduced, and then you stuff that together in a sausage. So it's not 100% anaerobic, right? There's still a little bit of oxygen there. A ham, on the other hand, you have a large hunk of meat that the Clostridium can get in because ham is injected with the solution. And so when you put those needles in, anything that was on the exterior can get on the interior. But once that's been injected, it is anaerobic. It's an oxygen-free environment. And so it's a perfect environment for either Clostridia to grow. And so it's most important of the three, really, to have the nitrites in the ham to prevent that growth. And so that's why the parts per million is a little bit higher in ham than the other two. So I also wanted to take this opportunity to get a little bit on a soapbox and talk some more about nitrites. This is not in the book, but I think it's important. So the biggest source of nitrite in the diet is not cured meats. It's actually leafy green vegetables, as long as you're eating your leafy green vegetables. So these vegetables are actually high in nitrate, not nitrite, but we have bacteria in our mouth and gut that quite easily convert nitrate to nitrite. And so as soon as you eat it, there's bacteria in your saliva that are converting the nitrate in your spinach to nitrite, and you're consuming it. Nitrite is then converted to nitric oxide in your gut. And nitric oxide is actually recognized to be beneficial to health. So they actually sell supplements that are beet supplements, usually, that are nitric oxide supplements. And it improves blood pressure and other things with your blood that make it beneficial to health. So the anti-nitrite movement, I think, is a little bit off. Okay. Now, nitrosamines. So if you are consuming these by themselves, you aren't consuming a whole lot of amino acids also, versus with meat, there are lots of amino acids. So that's maybe a little bit of the caveat. But in general, nitrite is not necessarily a bad thing for your health. So second part of the soapbox is that when you go to the grocery store and you see a sausage that says, or bacon or ham, that says uncured or nitrite free, these are not nitrite free. And unfortunately, it's due to a regulation that needs to be updated that says that if you aren't adding specifically sodium nitrite to the product, you aren't adding nitrite. And you have to label it uncured. So originally, the reason this regulation was written was because, well, nitrite protects our food. And if you aren't adding it, you need to label it uncured so your consumers know, hey, this isn't being protected by nitrite. But unfortunately, it didn't account for what would happen multiple decades later, where we're now trying to not have the ingredient sodium nitrite for labeling purposes, but in actuality, we are adding it in a different form. So all of these products have a different natural form of sodium nitrite that has been added to the food. It's the exact same chemical. It's just has a different carrier ingredient going into the product. So celery juice powder is, so they take the celery juice, they make it into a powder, they dehydrate it. It is high in nitrate. Then they put that into a vat where bacteria ferment it and convert the nitrate to nitrite. Okay? You get it into a powder. It's probably juice, then bacteria, then they get it into a powder. And then they add it at the same levels as the sodium nitrite ingredient. So they add it at equivalent levels of sodium nitrite that is in the celery juice powder and what they would normally add to the product. And so you get a cured, uncured product. So the key thing to know as a consumer, if you are trying to avoid nitrites or not fall for marketing gimmicks, which is not really a purposeful marketing gimmick. The meat industry likes it because it does help them with marketing. But the food scientists that are part of the meat industry that understand this are like, no, this isn't right. When I worked at Smithfield, all of our lead food scientists were like, this is stupid. We need to, like, the regulation needs to change. This is deceptive. Marketing people like it. But the true people behind the food science of the industry are like, yeah, this needs to change. But the key thing to know as a consumer is if it's cooked, if it's meat and it's cooked and it's pink, it has nitrite. It might be in some other form, like celery juice powder, but it has nitrite. Okay, so I think this is the last one. Antimicrobial agents, acids. Oh, no, there's one more after this. So acids prevent microbe growth by lowering the pH of food. And so there are several, some of the main ones here. Acetic, which is vinegar. Ascorbic, vitamin C. Citric acid, lactic acid. These are both very natural acids. Propionic acid, which is usually used, often used in the form of calcium propionate, and that prevents mold in bread. Sorbic and benzoic acid. Sorbic prevents molds in yeast. Benzoic prevents yeast and bacteria. Together, they're used in soft drinks to prevent all three. So different acids have different properties. They'll be used in combination or chosen one for whatever property of microbial that it will prevent. Essentially is the takeaway from all of this. Antioxidants. So there's this and then one more, I think. Actually, no, I have 15, 16, 17, 4 more slides. I'm way off. Okay. Antioxidants. So we just covered the microbial preservation. Now we're going to cover oxidative preservation. So antioxidants that we use to prevent oxidation. Why do we use it? So oxidation causes changes in color. We've talked about that with fruit and meat. It causes changes in texture. Also fruit. Maybe not so much the meat, but definitely in fruit or vegetables. Oxidation causes changes in texture. Obviously causes changes in flavor and nutritional value. So oxidized fats are not able to be used in your body. You're also exposing your body to free radicals, which are not great for you. So antioxidants are used as preservatives to protect the food from the changes caused by exposure to oxygen. And of course, free radicals. The antioxidants interfere with the formation of free radicals. And so free radicals, definition there, we've talked about it before, but these are unstable atoms or groups of atoms that contain one or more pairs or one or more unpaired electrons. The reason free radicals are bad from a nutrition and health standpoint is that they are related to aging and are carcinogenic. They're related to inflammation. Many people consider free radicals like this is why we age. And so I don't know if I've talked about it in this class before. I think I talked about it in my chemistry class. But so oxidation, oxygen. Okay, oxygen is reactive and often leads to oxidation. Oxidation or oxygen, what we need to survive, actually slowly kills us also because it leads to aging and then we eventually die. So it's kind of interesting. What we need to survive is slowly killed us. But the more free radicals that are in our body, the faster aging may occur and often can also lead to cancer. So the GRAS list of antioxidants include a few that we'll cover here. The first is vitamin C. And antioxidants work in different ways. So I'm going to go over some of the ways here. Vitamin C is a hydrogen atom or electron donor. So what that means here is I have this diagram. This is vitamin C here. And this OH here is a hydroxyl radical. If you look closely, you can see, okay, so you have paired electrons on top and bottom. On the side, there's an unpaired electron. There's a single electron there. That makes it a radical. What the ascorbate does is it donates one of its electrons, see here on this oxygen, to this radical. And that radical becomes a hydroxide ion, which is stable. And the ascorbic acid, it just kind of changes its structure to be stable again. So it has a radical here, right? There's an unpaired electron. It gives that unpaired electron to this bond, and there is a double bond here, and this oxygen gives that electron to that double bond there. Things get shifted around, and it actually has a radical here, so it can go back and forth. So it becomes a radical itself, okay? There is an unpaired electron here or here. But the key thing is that this radical is more stable than this one and is less likely to interact with something else and perpetuate the damage further, okay? So now the damage is just on the vitamin C and not within our bodies or within the food. Vitamin C is often added to processed meats to reduce nitrosamines and maintain color. So it prevents oxidation that can accelerate nitrosamine formation. Vitamin E is also a hydrogen atom or electron donor. And in this example, I'm showing you how it's going to donate a hydrogen atom. So here we have vitamin E, which is alpha tocopherol, and a hydroxyl radical. And what happens here is, make sure I'm looking at the right spot. Where is the, okay, I was trying to find the hydrogen that it's donating. So the hydrogen is on this hydroxyl group here, okay, and it donates it to the hydroxyl radical, which then becomes water. And then the vitamin E becomes a tocopheroxy radical. So it has that missing electron here. It's an unpaired electron here, but again is less reactive than what this hydroxyl radical is, and so it's less likely to cause any further damage along the line. Okay. Vitamin E can be regenerated by ascorbic acid, so it can interact with the ascorbic acid, and the ascorbic acid will give it a hydrogen, and then it becomes back to regular alpha tocopherol, and then it can continue to act as an antioxidant. It is added to processed meats to reduce nitrosamine. Oh, and the book says citric acid, but ascorbic acid is what it should be. And vitamin E is often added to processed meats to, like the vitamin C, reduce nitrosamines and maintain color. Okay, and then the third one we'll look at is citric acid, and this one works differently than the other two. It chelates metal ions. So metal ions are often a source of accelerated oxidation. And so if those metal ions can be bound up, that's what chelating is, it's just binding it up so it can't react with anything else, then it provides a protective effect against any further oxidation occurring. And so what this little diagram is showing here, this is the citric acid, this part on the left, and this is a big capital M representing any kind of metal ion. And so it's got an oxygen on both sides, and it's just binding up that metal ion so that it can't react with anything. Okay, so those were our GRAS antioxidants, and then next are our controlled use antioxidants. And so these include BHA, which is, you don't need to know the full name of this, but butylated hydroxyanazole, BHT, butylated hydroxytoluene, propylcalate, and TBHQ, which is tertiary butyl hydroquinone. So BHA and BHT have research showing negative effects at extremely high doses, which is much higher than what we consume. There is also some research showing that it's anti-carcinogenic. So there's some that's showing it can cause cancer at really high doses, and other research showing that it's anti-carcinogenic. So this is one that the research really doesn't agree with itself. I would just say there are more ingredients to just watch. They may be fine and actually good for us because in general, antioxidants are good for us, but they may not. And so out of maybe a little bit of a concern, but also public perception, because there are groups that see the negative research and are very vocal about it, a lot of companies have taken BHA and BHT out of their products. And so in a lot of formulations, they're not in the formulations anyways. So I would just know that these are a list of controlled use antioxidants, and you don't have to know the full names of the ones that have abbreviations. Okay, now this is the last slide. So sulfites, another type of antioxidant. These are regulated, are controlled use. So sulfites are a group of salts containing sulfur. So there's lots of different ones. And again, you don't need to know all of the chemical formulas for these, but there's sulfur dioxide, which is actually not a salt, but I guess it's just grouped in with the sulfites. There is sodium sulfite. So you have sodium and sulfite. There's sodium and potassium bisulfite, and sodium and potassium metabisulfite. So there's actually quite a number of of sulfites that can be used. And their usage is that they are typically added to frozen and or dried fruits and vegetables to prevent browning. So browning from our phenolase, right, that we've talked about extensively. So this is dried apricots, and so with sulfur dioxide, this is what we typically expect to see with your dried apricots, and without sulfur dioxide, they look like this. So just think about this. When you see white raisins, or the lighter colored raisins, what do you think they've done? Well, it's probably just this, right? Because raisins are dark, not because red raisins were used, but because of phenolase. And so if we use sulfur dioxide in the raisins, then they have a lighter color and they don't turn dark. So it's not anything more healthy or different type of raisins used with white raisins. It's probably just that there's some kind of sulfites added. So sulfites are banned from use in fresh produce because it would cause allergic reactions. I would say it's also probably banned because of one of the things that we talked about earlier, that it, well, maybe not, I don't know. It kind of doesn't make it fresh anymore once you've processed it and added sulfites. And so in some ways it would be a little bit deceptive marketing to use sulfites, would be my personal opinion. But some people are susceptible to reactions with sulfites, and so that is one reason that it is banned from use in fresh produce. So some people, like, they cannot eat dried fruits because of sulfites. It causes issues with their body. The sulfites must be declared if they are 10 parts per million or higher. So if they use them at a level that's less than 10 parts per million, they actually don't have to be on the label. One problem with sulfites is that they do destroy thiamine. And so in any foods that are a major source of thiamine, sulfites cannot be used. So that is where we will stop this week, and then next week we will cover the other 3 functions of additives and continue on with the rest of the chapter.